Welcome to Big Idea Hurdly, where you can learn something new in just a few minutes. Today, we study together Steve Nadis, Shing-TungYau's The Gravity of Math, How Geometry Rules the Universe, in which we probe into how geometry, once a mere mathematical tool, has become the key to understanding the deepest mysteries of the universe, from black holes to the fabric of space-time. Shing-TungYau is a mathematics professor at Tsinghua University and professor emeritus at Harvard University. Don't go away. Hurdly the editor will be right back with the story. Geometry, for centuries, was regarded as a practical discipline, essential for land measurement, architecture, and even art. But as we've come to understand, it's much more than that. Geometry has evolved into the language of the universe, a key to unlocking some of the most profound mysteries in physics. The authors delve deep into this transformation, showing us how geometry is not just about shapes and sizes, but about understanding the very structure of reality itself. One of the most fascinating insights in this book is how geometry laid the groundwork for Albert Einstein's theory of general relativity. Einstein realized that gravity was not just a force pulling objects together, but a geometric effect, the warping of space-time by mass. This realization came from his contemplation of how light travels through space and time. The authors highlight a poignant moment from Einstein's life when he imagined a man in free fall, feeling no gravity, leading him to the profound realization that gravity and acceleration are indistinguishable. This idea, known as the equivalence principle, was a key stepping stone in developing his revolutionary theory. In this context, the authors share a remarkable story about how Einstein struggled with the mathematics needed to formalize his ideas. Despite his genius, Einstein found himself at a crossroads, unable to proceed without the help of complex geometry. It was only after he reached out to his friend, mathematician Marcel Grossmann, that he could finally piece together the geometric framework necessary for general relativity. Grossmann introduced Einstein to Riemannian geometry, a type of non-Euclidean geometry that describes curved spaces, which was crucial for Einstein's work. This partnership between physicist and mathematician is a prime example of how geometry is not just a tool, but a key to unlocking the universe's secrets. As the authors put it, Einstein might have been the mind behind general relativity, but it was geometry that gave him the language to express it. Another powerful example of geometry's role in physics is the discovery of black holes. Black holes are regions of space where the gravitational pull is so strong that not even light can escape. The mathematics describing black holes is deeply rooted in geometry. The authors tell the gripping story of Karl Schwarzschild, a German physicist who, while serving on the front lines during World War I, found time to solve Einstein's equations in the context of a single point of mass. His solution predicted the existence of black holes, regions where space-time curves so intensely that it closes in on itself. Schwarzschild's work was a triumph of applying geometric principles to theoretical physics, showing how geometry can reveal phenomena that were once thought to be purely speculative. Moreover, the authors delve into the geometry of the cosmos on the grandest scale, describing how it shapes our understanding of the universe's structure. They recount the fascinating tale of how mathematicians and physicists collaborated to develop the concept of the cosmic microwave background, CMB, the afterglow of the Big Bang. This relic radiation, spread across the universe, is not uniform. Its slight variations are mapped using geometric tools, providing a snapshot of the early universe. These geometric patterns in the CMB have helped scientists refine the Big Bang theory and understand the large-scale structure of the universe, revealing the cosmic web of galaxies that span across billions of light-years. The authors emphasize that without geometry, such discoveries would remain beyond our grasp. One final story that underscores geometry's importance in understanding the universe is the ongoing quest for a theory of everything, a unified theory that reconciles general relativity with quantum mechanics. The authors describe the work of string theorists who rely heavily on complex geometries, including Calabi-Yau manifolds, to explore the nature of fundamental particles and forces. These shapes, existing in higher dimensions beyond our everyday experience, are crucial in the equations that could potentially unify all the forces of nature. The intricate dance between geometry and physics continues to push the boundaries of what we know, with the hope that one day it will lead us to a deeper understanding of the universe's most fundamental truths. As the editor of Hardly, by learning from these profound connections between geometry and the universe, we may one day chart courses through realities we have yet to imagine, revealing new dimensions of existence that are currently hidden from our view. In revisiting the powerful idea that geometry has become the key to unlocking the deepest mysteries of the universe, it's clear that the marriage between mathematics and physics has reshaped our understanding of reality. From Einstein's realization that gravity is a geometric effect to the role of geometry in describing black holes and the structure of the cosmos, the impact of this discipline is profound. One particularly compelling story from the book involves the mathematician Henri Poincaré, whose work laid the groundwork for chaos theory, a field that relies heavily on geometric concepts. Poincaré was tasked with solving a problem related to the stability of the solar system. While working on the problem, he discovered that the motions of celestial bodies are highly sensitive to initial conditions, leading to what we now know as deterministic chaos. This was an unexpected revelation at the time, showing that even in a deterministic system, the future is not always predictable. Poincaré's insights demonstrated how geometry could reveal the unpredictable nature of complex systems, a concept that has since been applied far beyond astronomy, influencing fields as diverse as weather forecasting and economics. As the editor of Hardly, by understanding how geometry governs the universe, we can start to see the hidden patterns in the chaos of everyday life, giving us the tools to navigate an increasingly complex world with greater insight and foresight.